Hello everyone. In this video we will develop an adekoCAM product model which is composed of multiple parts completely from scratch. An adekoCAM product is a collection of related or independent parts forming pieces of a certain design. This might be a wardrobe, a sophisticated door model that has a frame made out of multiple parts, or a toy having separate parts, 7 pieces tangram, or a chess set. A product can even be an entire kitchen or a full house too. In adekoCAM, the difference between a door and a product is that doors are always single parts. However, products can have arbitrary number of parts. Products are collections of parts. This collection might also have doors from the door library as well. In this video, we will connect two parts forming an L-shaped end product. First, I'm sketching on a piece of paper what I have in mind. We will be using a specific connector with a certain frequency to bind these two pieces. This connector requires holes on both the parts, forming the end product. I also think about what model parameters need to be settable by the library user. The margins from the edges, the distance between connectors, etc. Product programming interface is a superset of door programming interface. That means we can use all the commands we use to develop door models during product development as well, and build parts by adding new geometric features one by one. Once there is nothing more to add to the part, we can use pack into part command to encapsulate thus far created geometries within a part and start building the next one within the same model script. We will see this in a minute. Developing a product script might easily be a faster process compared to door development. This is because there are usually, but of course not generally, less number of geometric features or surface topological components in parts forming a standard product such as a furniture. On the other hand, a product might have many parts. In this video, we will directly go to the model directory and create necessary files to form a product model instead of using adekoCAM's embedded library. Now let's go to the product library of adekoCAM and create a directory named as aaa.product. Here the name of the product is aaa and all the products end with .product suffix. Go in this directory and create two ASCII files named as data.json and script.lua. Data.json is the ID of the model and script.lua is the model script you would remember from door development. Don't forget to take a picture of your hand drawing and to save as parameter image.png. Make sure the image is horizontal for convenience. This image will be visible on model parameter view. Let's form data.json as I kind of know what model parameters will be open to library user. The parameter named A is the distance between the connector centers given in millimeter with 32 as its default parameter. You must be familiar with this format as we use it during door development video as well. Other two parameters are also similarly entered as the margins from the edges. In case of problems, make sure the JSON format is correct. Variables are in double quotes and separated from their assignments with a semicolon. Lists are in square braces, just as in model parameters, and list members are written in between curly braces separated with commas from each other. The last member of a list does not have separating comma. This file is the ID of the model, and in case it cannot be parsed correctly, the library wouldn't function correctly. Now let's open the script.lua from within ZeroBrain. You can also copy this file from another model and empty it. Make sure you have already seen the door development video as we made an entry to Lua language syntax there. An adekoCAM product is mainly a function called product main. This function is now empty, so there is no part or model. We will build the model which is formed by two parts step by step. Let's start first with what the known things are. Even though we didn't declare explicitly ourselves, the dimensions of the final part are known as capital X, capital Y, and capital Z. Similarly, the body and door materials as well as their thickness values are also known in this development environment. We will utilize these parameters as necessary. First, the model parameters are to be declared. These are the parameters we would like the library user to control in order to create different end products. After declaring them, we should make them modifiable. We used this same method in door development as well. Now we can build the first part. I personally add this part shape simple ASCII art to make the script more readable. It does not have any effect on the model at all. First, declaring a few things related to what the part is. Name of the part, its description, should the material grain be taken into account, whether or not this specific part is a door. If the part is declared as a door, features of the door model user selects are added to those we will be creating here. Our parts are not doors, so they will only have the features we will be creating here. An important difference between door models and product models is the dimension consideration. End product dimensions are not supposed to be identical to the dimensions of the current part in product models. As an example, the part width of the current part we are building is not equal to the width of the end product, but it is material thickness less than it. You can easily understand why this is the case if you have a look at your hand drawing. This is an important point, as the width of the part might be identical to the width of the end product if the part is, say, the base. However, it is not the case for the side parts. The width of a side part is the depth of the product, or equivalently the capital Z. We will see this while building our second part, as it is a side part. After the declarations, we create the part shape on the sizing layer automatically by makePart command. Since we will be producing both the materials out of body material, we should give body material thickness as parameter to set thickness command. Now let's finalize this part, which is currently just a rectangle, by packIntoPart command. I'm adding the following lines. packIntoPart command will take the following parameters and finalizes the part construction. Whether the part is a door, should material grain be taken into account, description of the part for the labeling step, dimensions of the part, unique part name, material of the part, and finally individual edge band layers as well as their thicknesses. The reason why this command is within an if statement is that an error message can be generated for the library user in case the part cannot be created due to some errors. Otherwise it would go unnoticed, which would be a problem for the library users. This is the bare minimum for a product part. Let's now add connector holes as well as groove or channel, setting layer name and depth for the coming geometries. We cannot know how many connectors are needed as we cannot know the height of the end product. So we need to calculate this value based on what is known. If I subtract the two margins from the height and divide this value by the difference between the connectors, this should give me the number of connectors minus 1 as a result. Now, using this value, we can create that many connectors in a loop parametrically. This is one of a few methods to write a loop in Lua. This syntax means increase the value of variable I from 0 to how many one by one and run the command in between do and end. So we will be creating how many plus 1 many connector holes by employing the hole command, which takes as its first parameter a point as the center of the hole, radius of the hole as the second parameter, and depth of the hole as the third. Let's now create a channel, once again setting the layer name and depth for the coming geometries. This time using the command groove, I'm creating a channel. This command takes as its first two parameters 2 points in between the line will be drawn and draws a line in between these 2 points at the depth given as the third parameter. Let's assume the groove has a 40mm offset from both the edges. These are all the geometries we need to create on the first part. The first part is completed as the next command finalizes the part building cycle. We are at the same point where we started to build the first part. We can now start building the next one just as we did for the first one. Let me summarize the part building cycle here once, as this is basically all we need to repeat to build products. In between declarations and finalization with packIntoPart is the set of commands for creating geometric objects such as holes, grooves, pockets, etc. This sandwich is repeated for each of the parts forming the final end product. Once we have as many sandwich as needed, the script returns true and the model terminates. Let's have a look at how our part looks like. As you can see, the connector holes as well as the groove are as expected. In case the product height increases, the number of holes as well as the length of the groove should follow. Let's test this. Open the script called adekoProductMod.lua, which is found in Lua library in adekoCAM's root. This script is used to simulate user input such as product dimensions and model parameters. We can use this script to test our models against being parametric, among other things, increasing the Y value and rerunning the script to see the adaptation. As you can see, the part nicely follows the change in product dimensions. Let's get back to where we were. Starting the sandwich this time for the second part, adding my personal part-shaped commanded lines to increase the readability of the script, declaring standard set of variables this time for the second part, creating the part shape and terminating the part just as we did for the first one before. Now the breads of the sandwich are there. I'm placing my cursor just before the termination command pack into part and start creating the corresponding connector holes as well as the groove. Since the number and the center coordinates of the corresponding holes are the same math phrase as well as the loop will be used, so I can just copy what I did for the first part as well. The only difference would be the hole sizes, as the corresponding holes on the second part have diameters of 2.5mm instead of 10 here in the second part, creating the groove on this part as well. The second part is also complete. Let's run the model and see how it looks like. Right now, both of the parts are drawn on top of each other. We can easily see that the holes perfectly correspond to each other. As we set in ADeko product mode the product dimensions, the parts have corresponding dimensions. The first part is narrow and the other part is wider, as the depth of the end product sets its width. Product model is complete. Now we can return true to terminate model script. Let's send the product to a project cut now and see parts in the cut plan. As you can see, our 2 parts product can easily be produced. Now let's send a few more products with varying model parameters as well as sizes into the same project cart. Populating the product list and modifying the model parameters for each line. As you see, we can easily create products out of the model we just developed with varying parameterizations. In this video, we developed a multi-part adekoCAM product from scratch. Using the same method, you can develop your own library of end products for your standard items and easily send instances out of them directly to CNC machines. Thanks for your attention.